Hello everyone. In this session, let me continue the theorems on non-measurable set, as we already studied non-measurable set in previous session. However, here is a statement statement of the theorem. There exists a non-measurable set in closed interval 0 and open interval 1. So we have to prove that there exists one non-measurable set in this interval. So before going to the proof, let me revise the concept of what we say equivalence relation. So we can prove this statement by defining a equivalence relation. It is a symbol for representing equivalence relation. Hope so you remember this. So this we have to define a equivalence relation in this particular interval 0 1 by taking any two elements in the given interval. So when do we say relation is equivalence relation? When it satisfies reflexive, symmetric and transitive. Reflexive in the sense when you are going to consider two elements you are going to consider one element in a given set. If the same ordered pair repeats, then it is reflexive. Symmetric in the sense if an ordered pair AB is in a relation, then BA should be there in a relation. So you have studied all these concepts in your PU also. So for transitive, if AB is in a relation and BC is in a relation, then as per the transitive rule, AC should be in also R. Then we can say it is transitive. So remember, for reflexive you are going to take one element, for symmetric you are going to take two elements in a given set. Then we are checking whether BA is there or not. Next, for transitive we are going to take three elements, as I said. So ABC, we are going to check whether if AB BC is there should exist AC in a given relation. If all these three conditions satisfy, we can say that is equivalence relation. Now what I have done is I have to prove there exists one non-measurable set in this interval. So let me define an equivalence relation in this interval, and let me take two elements in this interval. I'll define a relation in this interval as x minus y is rational number. Rational number in the sense any number which is of the form p by q. Fine. I have defined a relation such that x minus y is rational number. I'll give you one more example for relation. Like suppose if I have a set A such that it contains an element 1, 2, 3. I can define a relation R such that x minus y, x comma y belongs to A. X minus y is equal to 0. In the sense, suppose if I have like 1, 2 repeated times 3. So only element belongs to R is 3, 3. Right? Why? Because 3 minus 3 will be 0. It's satisfying the condition of a relation. Likewise, I have defined this relation as x minus y is a rational number. I have to take two numbers such that the difference will be rational number. So in such case, we can define an element will be in our given relation. First, let me prove for equivalence relation. Let me prove it is reflexive. So when do we say reflexive? Let me take one element in the given interval. It is x. So as per the reflexive definition, if I going to take element A in a set, I have to repeat that. In the sense I have taken x. So how the relation is defined? X minus y. So I have to calculate x minus x. So obviously whatever may be the value of x minus x will be equal to 0, right? Again 0 is a rational number. Why? Because any number can be expressed in the form of p by q. So it is a rational number. Meaning is x comma x is also belongs to R. Why? Because the relation is defined as x minus y is a rational number. Since a difference is a rational number again, so it belongs to a relation that what we have defined here. So we can say x is related to x, so it is reflexive. Second, let me prove it is symmetric. So to prove symmetric, as I already told you, basic says that to prove symmetric I have to choose two elements. So let me take two elements x comma y in the given interval. We have to prove, suppose if x related to y, x is related to y only when this condition satisfy, right? When x is related to y, I can write x minus y is rational number. Fine. So I have to prove that y is also related to x. As per the definition of symmetric, if AB is related, BA should be related, right? So xy is related, so this condition holds good obviously. Then I have to prove BA is also related. In the sense y is related to x, I can write y minus x is also rational number. Fine. If you want, you can take any counter example. If you subtract two rational number, again you will get back a rational number. Though suppose if you're going to take 1 by 2 minus 1 by 3, after taking LCM you will get by P by Q only. Even though if you're going to get only element P, you can express that as Q. For example, when I have an element 2, definitely 1 will be there in the denominator. So any number can be expressed in the form of P by Q. So again I can say y minus x is a rational number. Meaning of this statement is x is related to y. In the sense xy belongs to R. So y minus x is also rational number. I can say y is related to x. So therefore it is symmetric. Clear? Anyhow, I have proved reflexive and symmetric condition. Let me prove transitiveness. So I have to prove equivalence relation is transitive. So for transitiveness, I have to choose 3 elements, say x, y, z, in a given interval 0, 1 and closed open interval 1. So as per the transitive relation, if x is related to y and y is related to z, I have to prove that x is also related to z. Let me check. If x is related to y, I can write y minus x is x minus y is equal to a rational number. Say that as R1 is a rational number. Fine. If y is related to z, I can write y minus z is equal to R2 is again a rational number. If you want, you can take any counter example. Fine. Again, it is a rational number. So if that was the case, x minus z, how can I write x minus z as? I can write this as, let me write x as x minus y plus y minus z. So minus y plus y get cancelled. Again you will get x minus z, right? So x is related to z, meaning is x minus z. So I can write x minus z as x minus y minus z. What I have obtained for x minus y, it is rational number. Y minus z is R2. So we know that sum of rational number is again a rational number. So therefore I can write x is related to z. So it is just a logic. So what I have proved is x is related to y is related to z. Then I have proved that x is also related to z. Therefore I can say it is transitive. Since it can satisfy all the 3 conditions, reflexive, symmetric and transitiveness, therefore I can say it is equivalence relation. The symbol is equivalence relation. Equivalence relation in a closed interval 0 and open interval 1. Fine. This is just an axiom which helps us to prove further statement, that is there exists non-measurable set in 0, 1. Just what I have proved is whatever the element that you are going to choose in this particular interval, that will satisfy all these 3 conditions. Thereby I can say it is an equivalence relation. Now by using this axiom, let me prove the given statement as we can choose a set R, or let me take a set as P, which can be exactly having one element from each equivalence class. In the sense, what I'm trying to say is, just now what I have proved is, in this particular interval, whatever the elements you are going to choose, it satisfies all these 3 conditions. I can say it is reflexive. So let me take P as a class of equivalence set. In the sense, it contains set of equivalence classes or equivalence relation, I can say. Fine. P contains a set of equivalence relation. Let me take that as x1, x2, x3 and so on. Fine. And further we can express closed interval 0 and 1 as union of all these equivalence classes, right? What I'm trying to say is, just now I have proved it is an equivalence relation. In the sense, I can express, if you take 2 elements in this particular interval, it's satisfying all the 3 properties of equivalence relation, right? So we can say this interval consists of, say, class of equivalence relation. Let me take that as P. So P is what we say, P can be found by exactly one element such that it contains equivalence classes. In the sense, it can be expressed as a set of equivalence classes. Meaning is, I can express a given interval as union of all the equivalence classes. Whatever the element that you are going to take in this particular interval, all the elements will be satisfying the conditions of equivalence relation, that is reflexive, symmetric and transitive. Fine. Thereby I can write that P is also subset of 0, 1. Right? I'm trying to express this once again. See here, what I have done is I have proved it as equivalence relation. So I can express this as union of all the union of all the equivalence classes. Since P is containing set of all equivalence classes, again 0, 1 can be expressed as union of all the open classes. For at least some particular point, it may contain all these elements, right? So I can write P and 0, 1 is subset of each other. Fine. Now it is enough to show that P is non-measurable, or we can say P is non-measurable set. That is what we have to prove. There exists non-measurable set in 0, 1. Meaning is, what I have done is I have expressed a P as subset of 0, 1. If it is enough to show that if I prove P is non-measurable, I can say 0, 1 is also non-measurable. Why? Because as P is subset of 0, 1, I can say that if I prove P is non-measurable, I can say 0, 0, 1, or closed interval 0 and open interval 1 is also non-measurable. So I am using that logic. So let me prove P is non-measurable. Fine. Now let me take Ri such that I is equal to 0 to infinity b, a set of all enumeration of rational number. In the sense it contains a set of all rational numbers within the interval 0 and 1. Fine. Now let us define pi as p translation modulo ri for each I. I have defined one of the element pi. Why? Because translation modulo is one of the non-measurable set. So let me define pi as p translation modulo ri for each I. Since what I have chosen is P is subset of closed interval 0 and open interval 1. Obviously, one of the element Pi, let me write once again, Pi is also subset of 0 and open interval 1. Further, I can express all the, whatever the existing Pi is there, that will be definitely subset of 0, 1. Why? Because this is already proved in the above statement. Now this will be obvious for at least one of the I. This condition will be holds good. Now I can express, if you are going to consider all those possible Pi values, definitely that will be the subset of closed interval 0 and open interval 1. Further, I can say Pi's are all mutually disjoint sets. In the sense there should not be any common element, right? Why? Because as it is subset of 0, 1, so as I said 0 to 1, it includes 1, it doesn't include it includes 0, it doesn't include 1. Why? Because I have closed interval 0 and open interval for 1. There will be no common element between 0 and 1. So since P is subset of 0, 1, I can say P is mutually disjoint as there is no common element. Fine. If that was the case, so I have already told you that Pi's are mutually disjoint. Let me take an element X belongs to some Pn intersection Pm. So I have chosen an element which belongs to this set. Meaning is that n is not equal to m. In this case, both the values are not equal. In the sense, x belongs to different set. Meaning is x belongs to Pn. Intersection I have written. So, and I have to write common. Why? Because x belongs to intersection. Intersection meaning is x belongs to Pm also. Clear? Now, let me express x in terms of translation modulo. As x belongs to Pn, I'm repeating once again, as x belongs to Pn, what we have defined Pi as P translation modulo Ri. So here in place of I can replace Pn, right? So I can, since x belongs to Pn, meaning is that I can express an element x as some element y translation modulo Rn. Just I have replaced an element P with y as per the required proof. So let me take x as y translation modulo Rn. So for y belongs to P, I am clearly mentioning here P is reference to set. So I have taken one of the element in this particular set. So I have written y here. Instead of R I have chosen ny because in place of I what I have Pn. Similarly I can write, since x belongs to Pm, I can write x is equal to z translation modulo Rm as z belongs to P. As per the definition, z is also one of the element of P what we have defined here. Clear? Now, how can I write, since here LHS values are equal, right? So by comparing these two equations, I can write y translation modulo Rn is equal to z translation modulo Rm. Clear? Clearly y and z will be element of same set P. This is what from the assumption, right? Now you can clearly note that here y translation modulo Rn and z translation modulo Rm, when you're going to take a difference, anyhow Rn and Rm are rational numbers, right? So I have already told you Rs are a set of rational numbers, so it is rational number. When you're going to take a difference, again you will get a rational number, because difference of rational number is again a rational number. Thereby I can write y is related to z. Why? Because what I have defined a relation at the beginning is, relation is defined in such a way that difference of element is rational number. What I have arrived is, since when you're going to take a difference, clearly Rn and Rm are rational number. As per this set, I have chosen these two elements from this set. So they are rational number. Again, when you're going to take a difference y minus z, again they will be rational number. I'll just write here y minus z is rational number. Reason it is. So I can write y is related to z. If y is related to z, I can clearly write Rn is equal to Rm. Right? In the sense, the difference is rational number. It is equivalence relation. So I can write Rn is equal to Rm. If this is the case, I can write Pn as P translation modulo Rn. as per the definition what I have defined is, see here what I have defined Pi as P translation modulo Ri. So similarly Pn I can write it as P translation modulo Rn. Similarly what can I write PM as P translation modulo Rm, right, as per the defined statement. Now what I have proved is Rn is equals to Rm. So I can write this as P translation modulo Rn can be replaced by Rm. Now I can replace this value by Pm, right? Fine. So Pn is equal to Pm. What I have proved is Pn is equal to Pm. But it is contradiction. Why? Because what I have assumed is Pns are mutually disjoint. Pi's are mutually disjoint in the sense there should not be any common element. Since Pn and Pm are one of the element of Pi and they are equal. Mutually disjoint meaning is no two elements are equal. No two elements are same. But here we have obtained a contradiction. Therefore, I can write it is not possible. In the sense there the no two element of the given set are equal in Pi's. Therefore, I can clearly write that Pn intersection Pm should be equal to null set, because as we assume that they are mutually disjoint, they cannot be equal. So I can write Pn intersection Pm is equal to null set for n not equal to m. Now what I'm going to take is, let me take one of the element in the same interval and such that this x will be in a y, and again let me take one more element y in the same interval. From these two assumptions I can say x comma y both the elements are in 0 comma it is open interval 1. Clear? If x comma y is in this open interval, I can clearly say as per the definition of translation modulo, x translation modulo y will be in the same open interval, same interval, closed interval 0 and open interval 1. Now let me take an element z which belongs to P intersection y. So what I have defined P as Pi plus, translation modulo Ri. Now I have taken an element z in P intersection y. Now if this was the case, I can write z will be in P and z is also in y. As z belongs to their intersection, it will be present in both the sets, I can say. This implies that I can say that z is related to y. As we proved in the previous case that y is related to z. So in the same case, in the same sense, I can write if z belongs to P and z belongs to y, I can take the difference of those. Again it will be a rational number, so I can write z is related to y. Similarly, if I'm going to take z belongs to P, x belongs to y, I can write x is congruent to y. See here, when z belongs to y, the minute when I write z belongs to y, I can write z is congruent to what we say the symbol equivalent to y. Similarly, when I write x is belonging to the same set y, I can write x is equivalent to y. So I can write, see here, by applying the translation property, I can write transitive property x is related to z as well. Why? Because at the beginning itself we have proved that whatever the equivalence relation we have assumed, it is satisfying reflexivity, symmetric and transitive. So as z is related to y, meaning is y is also related to z, y is also related to x. Removing the common element by transitive property, I can write x is related to z. So x is related to z meaning is, what is the relation I have defined? Two elements will be related only when their difference is a rational number. Thereby I can write x minus z is also, when it is related, I can say x minus z is rational number. Now let me take that rational number as, say, Ri. Fine. Now x will be shifting this, you will get z plus Ri, where z is an element of P. That is what I have assumed at the beginning. Clear? Now I can write, since z is an element in P, Ri is a rational number. What we have defined a set P as P plus Ri. Right? So P is P plus Ri. Again z will be an element of P. I can write this whole element will be in P. This whole element will be in Pi. Why? Because what I have assumed Pi as P plus some Ri. Since z is an element of P, in the sense this is of the form P plus some rational number. P plus some rational number is assumed as Pi. So I can write this element will be in Pi. Clear? This implies I can write as x is equivalent to z. What I have proved is x is equivalent to z. In the sense both are equal. See, if I express z plus Ri, which is an element of Pi, since they are equivalent, I can write x plus Ri is also in the same Pi. Clear? Or else for some rational number I can write x belongs to pi. Why? Because Ri is always a rational number which is in pi, obviously, as we define pi as p plus some rational number. So x belongs to pi. Clear? Now meaning is that I can express x belongs to union I pi. Fine. In the sense x is an element of where I have chosen, see here, what I have chosen is x belongs to this interval 0 1. So I can replace x with the interval 0 1 belongs to union I pi. Fine. I can write like this by the assumption. Let me take this as equation 2. And let me take where I have assumed here. So let me take this as equation 1. Fine. Now let me compare equation 1 and 2. Look at equation 1, what we have taken, p is subset of 0 1. What we have arrived is 0 1 is belongs to pi. Belong meaning is it will be subset. So reverse inequality I have obtained. So from 1 and 2, what can we write? 0 1 closed interval 0 open interval 1 will be equal to union I pi. From equation 1 and 2 we can write like this, or else write I is equal to 0 to infinity pi 1 and the same. Fine. Why? Because I have arrived at both the inequality, so thereby I can write like this. Clear? Now suppose p is measurable. If this that what I have done is I have expressed this interval as union of all the pi's. Now suppose if p is measurable, I can say pi is equal to p translation modulo Ra is also measurable. This theorem I have proved in the previous session. You just go through that. So if p is measurable, I can say its translation modulo p translation modulo Ra is measurable. In the previous session I have proved one theorem. Go through that. See something like if open set E is measurable, then E translation modulo Y is measurable. I have proved that. So by that theorem I can say if p is measurable, if pi is equal to p translation modulo Ra is also measurable. Measurable. Now let me take measure on both sides. So measure of pi will be equal to measure of p translation modulo Ri. So p translation modulo Ri can be written as p. As per our assumption, I can write this as p. Why? Because obviously when I say p, p contains a translation modulo. Like in the previous session itself I have explained. Suppose if I have an element e, this is from the previous session. So x plus y, I can express this as x translation modulo y, where x is one of the element in E. Likewise, p is one of the element, p translation modulo Ra is one of the element of p. So I can express pi as measure of p. Fine. Further, so as a written measure of pi is equal to measure of p, what we have assumed is p as closed interval 0 open interval 1. So I can write a measure of pi as measure of 0 1. Why? Because p is assumed as closed interval 0 and open interval 1. Further, this can be written as all unions of y, because p translation modulo Ri can be written as pi. So I can rewrite this as union of all pi's. P as pi is p translation modulo Ri, I can write this as measure of union of pi's. Clear? Now measure of closed interval 0 1, measure in the sense it is a length, right? So length of 0 minus 1, obviously length will be positive, so I am going to take it as 1. 1 is equal to summation over I can write this as measure of pi. Fine. Suppose if measure of pi is equal to 0. Suppose if this value, measure of this value will be equal to 0, then what happens to the above equation? 1 is equal to 0. Obviously it is not true. Am I correct? Why? Because length of 0 1 is 1. So if the value of this is equal to 0, I have obtained the monotonic property, so union becomes summation. If this value is 0, I have obtained 1 is equal to 0. So which is not possible. So conclusion is that measure of pi should not be equal to 0. In the sense this value should not be equal to 0. In the sense that value should be greater than 0. Clear? Greater than 0 meaning is that I have obtained this value as value. I can express this equation as, suppose if it is greater than 0, I can write for greater values it will be infinity. 1 is equal to infinity for larger number. Anyhow, which is also not true. Is 1, I cannot express 1 as infinity. I cannot express 1 as 0. So it cannot be possible. Fine. I can write which is not true. Which is not true. Clear? Meaning is that if measure of pi is equal to 0, then also we have arrived a case which is not true. If it is greater than 0, then also we have arrived the case that it is not true. Then the meaning of that is P is non-measurable. P is non-measurable set. Clear? What I have done is I have assumed that suppose P is measurable and let me take measure of P as 0. If measure of P as 0, I have assumed this based on the concept that P is measurable. Suppose if P is measurable, either it may be equal to 0 or it should be greater than or equal to 0. If it is equal to 0, then 1 is equal to 0, it cannot be possible. If it is greater than 0, we will obtain 1 is equal to infinity, again it is not possible. We have arrived at a contradiction. Therefore, what I have assumed is wrong. That is P is not measurable. What I have assumed is P is measurable. I have arrived at a contradiction. Thereby I can say P is non-measurable set. So that is what I have to prove is, see here, there exists a non-measurable set in 0, 1. I have to prove there exists at least one non-measurable set in 0, 1. So what I have assumed is P is subset of 0, 1. So if P is non-measurable, I can say there exists at least one set P which is non-measurable in this particular interval. Hope it is clear. Please go through the concept that I have explained. First I have proved that prove the equivalence relation, that is it is reflexive, symmetric and transitive, and I have use the same concept to prove by using translation modulo. Go through the theorem. Further, if you have any doubt, I'll let you clarify. Thank you. Continue in the next session.